There is an asteroid out there with a date already circled on our calendar, and the people who know it best have a strange and uneasy relationship with that date. They can tell you where this rock will be on a single Friday evening 4 years from now, down to the kilometer and very nearly the minute. They have tracked it for more than 20 years. And yet, if you ask them the simplest, most human question about it, what is it really, what is it made of, what will it do, they go quiet. Because the honest answer is that they do not entirely know. The closer we look at this object, the stranger it gets. It appears to be too light to be solid. It tumbles through space in a way that a simple rock should not. And in 2029, it is going to fall past the Earth so close that it will slip beneath our own satellites, close enough that our planet's gravity will reach up and take hold of it for the first time in perhaps millions of years. Now, here is the thing I want to settle for you right away before we go a single step further so that you can let your shoulders drop and stay dropped. It is not going to hit us. That has been ruled out for the next 100 years, and I would never spend these quiet hours with you pretending otherwise. The unease has nothing to do with a collision. It is something far more interesting than fear. It is the suspense of a one-time experiment that nobody alive can predict the outcome of, performed on the most studied dangerous rock we have ever found, in front of the entire world, with no rehearsal and no second chance. Picture the evening itself for a moment, because it is not what most people imagine when they hear the word asteroid. After the sun goes down across Europe and Africa and the western edge of Asia, a new point of light will appear among the familiar stars, and it will not behave the way a star behaves. It will move. Not with the blinking rhythm of an aircraft and not with the silent glide of a satellite, but with a steadiness and a speed that your own eye can actually follow, drifting across the constellations over the course of a single night, brighter than almost anything else up there. And the quietly astonishing thing about that light is that it will not be a light at all. It will be a rock. A rock larger than a cruise ship and older than the Earth itself, and roughly 2 billion people will be able to stand outside and watch it cross the sky with nothing but their own eyes. That is where we are going tonight. We are going to spend the next couple of hours with this single object, a piece of stone and dust that carries a name borrowed from an old story about chaos, and a date already fixed on the calendar. We are going to follow it all the way from its birth in the earliest days of the solar system to the night it first appeared on our screens with a number beside it that frightened some very serious people. And we are going to walk slowly through exactly what is going to happen to it, and to us, on that Friday evening, the 13th of April in the year 2029. This is not, in the end, a story about an asteroid that is going to strike the Earth. It is a far stranger and, I think, a far more beautiful story than that. It is the story of how we came to know almost everything about where a thing will be, and almost nothing about what it actually is. Masters of the orbit, strangers to the object. So I am going to ask you to hold one question in your mind as we go, because everything we look at tonight is going to circle back to it. What is actually inside this rock? Not its orbit, not its surface, but its hidden interior, the part no telescope has ever seen and no spacecraft has ever touched. Because the answer to that one question, it turns out, is the answer to almost everything else. Before we settle in, let me ask one small thing of you the way I always do. If you find a kind of calm in these long, quiet walks through the science of the night, then take a moment to subscribe, but only if you genuinely enjoy what happens here. This is a small channel, and every single person who chooses to stay makes a real difference. And if you would, leave a comment and tell me where in the world you are listening from, and what time it is for you right now, because I love picturing all the different dark rooms and quiet corners of the planet where these stories are unfolding at the same moment. Then dim the lights, get comfortable, let your breathing slow, and let us drift together out past the satellites and into the path of the visitor we have been waiting for. Begin with the rarity of it, because rarity is the whole reason any of this matters. Small rocks pass between the Earth and the Moon all the time. Objects the size of a car or a delivery van slip through that gap on a regular basis, and most of them we never even notice until they are already gone, if we notice them at all. They are simply too small and too dim and too quick. But an object the size of the one we are following tonight, something that spans somewhere between 300 and 400 meters across its longest dimension, coming this close to the surface of the Earth, is an entirely different category of event. A body of that size only passes this near to our planet roughly once every several thousand years. That is not a once-in-a-lifetime occurrence. That is once in the entire span of human civilization. The last time something this large came this close, there were no cities and no writing, no telescopes and no one with the faintest idea of what they were looking at. We are, as far as anyone can tell, the very first generation of human beings who will get to witness an event like this while actually understanding what it is. That alone makes the coming flyby one of the rarest pieces of cosmic theater our species has ever been handed. And I want you to hold the scale of the approach in your mind, because the numbers are difficult to feel until you anchor them to something. At its closest, this asteroid will pass a little under 32,000 kilometers above the surface of the Earth. To put that somewhere you can actually picture it, the ring of satellites that carries a great deal of our television and our weather data and our communications orbits at roughly 36,000 kilometers. The asteroid is going to come in beneath them. It is going to thread the gap between us and our own technology, passing closer to the ground than the highest things we have ever parked in orbit, at about 1/10 of the distance to the Moon. On the scale of the solar system, where distances are measured in the hundreds of millions of kilometers, that is not a near miss in any comfortable sense of the phrase. That is a brush against the skin. And what makes it almost unbearable in its strangeness is that we have known about this brush for a quarter of a century, and we can predict the moment of it down to the kilometer and very nearly the second. Picture then what that evening will actually look like, because it is not what most people imagine when they hear the word asteroid. There will be no fireball. There will be no streak of fire, no glowing tail, no thunderous arrival. This object is not going to enter our atmosphere. It is going to pass above it, far above the layer of air where shooting stars burn. What you will see instead, if you are standing under a clear sky in the right part of the world, is a single steady point of light, like a star that has somehow come loose from its place and decided to wander. Over the course of about an hour, it will travel a noticeable distance against the fixed background of the constellations, moving quickly enough that if you glance away and then look back, it will have shifted. It will move across an enormous arc of the sky in the span of a night, gliding from one region of the heavens to another. And it will be brighter than the stars that form the handle of the Big Dipper, brighter than almost anything else in the dome above you. Roughly 2 billion people across much of Europe and Africa and into Western Asia will be able to see it with nothing but their own eyes. No telescope, no binoculars, just a dark sky and the willingness to look up at the right time. The show will not be quite the same everywhere, and there is a geography to it worth understanding, because where you stand on that night decides what you get to see. At the peak of the encounter, the best seats belong to those across Europe and Africa and the western parts of Asia, who will catch Apophis at its brightest as it makes its closest approach. As the night wears on and the asteroid begins to recede and dim, the moving light will become visible from other parts of the world, drifting eastward into view for observers in parts of South America. And the motion itself will be remarkable. Over the course of that single night, the point of light will not merely inch along. It will travel an enormous arc across the heavens, sweeping through one constellation after another, crossing a span of sky far wider than most people ever watch a single object move in an entire lifetime, all in the space of a few hours. At its quickest, it will cover ground at a pace you can genuinely perceive, a star that refuses to hold still. There is something almost tender in imagining it, the same light crossing the same sky, witnessed at slightly different moments by people in wildly different places, each of them looking up at the same ancient piece of rock as it threads between us and our machines. And here is a detail that often gets left out of the telling, one that makes the geometry of that night even richer. The Earth is not the only world Apophis will pass close to on this trip. On the same passage, the asteroid will also have a close encounter with the Moon, sliding by our companion at a distance of roughly 90,000 kilometers. That is far less dramatic than its brush with the Earth, and the Moon's gentle pull will do little to the rock compared to what our own planet has in store. But it is a reminder that this is not a simple straight line drawn past a single point. It is a genuine threading of the needle through the Earth and Moon system, a path so precisely known that we can describe both close passes years in advance, and so finely balanced that the same gravity which will reshape the asteroid's spin will also, in the process, permanently enlarge the orbit it travels, sending it back out into the dark on a slightly wider loop than the one that brought it to us. And here is the part that quietly raises the hair on your arm. For an object that far away to appear that bright to your naked eye, it has to be genuinely enormous, and it has to be very close. Think about the size of it for a moment. Somewhere around 340 meters at the low estimate, possibly closer to 370 or even 450 along its longest axis, depending on whose measurement you favor. That is longer than 3 full football fields laid end to end. Stand it upright and it would tower over the Eiffel Tower, over the Empire State Building. This is not a pebble drifting harmlessly by. This is the kind of object that, in some other version of history, on some other trajectory, would be remembered as a catastrophe. It is precisely the size of thing that frightened us so badly when we first found it, and it is precisely the reason that, even now that we know with certainty it will miss, the entire scientific world cannot quite look away from that Friday in 2029. So sit with the peculiar shape of our situation. We have, in effect, scheduled an appointment 4 years into the future with a mountain of rock falling out of the dark. We know where the visitor will arrive almost exactly. We know the minute it will stand at its closest. And yet, when it comes to the far more intimate question of who or what is actually arriving, of what this thing is truly made of on the inside and how it will behave when our planet reaches up and takes hold of it, the honest answer from the people who have studied it longest is that they are not entirely sure. They have measured the path with a precision that borders on the miraculous. They have barely begun to know the traveler. And rather than simply admire the view that night, they are quietly preparing to treat the whole event as something far more interesting than a spectacle. They are going to treat it as an experiment. The Earth will be the apparatus, and this ancient rock will be the specimen, and the result is one that nobody, not the modelers, not the mission planners, not the people who have followed this object for 20 years, can promise in advance. The object has a name, and whoever settled on it was not in a gentle frame of mind. It is called Apophis. The name comes from the old Egyptian stories, where Apophis, sometimes written as a pep, was the great serpent of the underworld, the embodiment of darkness and chaos and dissolution. In the myth, the serpent lay coiled in the dark each night, waiting to swallow the sun and unmake the world, and every morning the sun had to fight its way past the serpent and rise again, and every night the battle began once more. That is the name we hung on this rock. And in a detail so neat that no storyteller would dare invent it, the day it makes its closest approach, the day the serpent comes nearest, falls on a Friday the 13th. We will come to how it earned that name, and the surprisingly playful story behind the choice a little later. For now, simply hold the image. A serpent of chaos with an appointment on Friday the 13th, and a planet quietly setting up its instruments to meet it. But before any of that, before the discovery and the scare and the experiment, I want to take you much further back because to understand what this object is, you have to understand where it came from. And it came from the very beginning. The story of Apophis does not start in 2004, when human eyes first caught it. It starts about 4.5 billion years ago in the chaos that preceded the planets, when the sun was newly lit and the space around it was filled with an enormous flattened disk of gas and dust, slowly turning. That disk was the raw material out of which everything we know was eventually built. The ground beneath your feet, the iron in your blood, the water in the oceans, all of it began as tiny grains drifting in that disk, colliding, sticking, clumping together into larger and larger bodies over millions of years. Some of those bodies grew large enough to become the planets. Most of the material was eventually swept up into worlds or flung out of the system entirely or pulled into the sun. But not all of it. In certain regions, particularly in the broad gap between Mars and Jupiter, the building never quite finished. The gravity of the giant planet Jupiter, enormous even in its infancy, stirred that region so violently that the leftover pieces could never gather themselves into a single world. They were doomed to remain forever as fragments. Pieces of a planet that never was. Those fragments are the asteroids, and Apophis is one of their distant descendants. It is, in the most literal sense, a leftover. A scrap of the original construction material that built the Earth, preserved almost unchanged across the entire history of the solar system. When you look at it, you are not looking at something that formed recently or that came from somewhere exotic. You are looking at a relic from the oldest chapter of the story, a sample of the same stuff that, in a more fortunate location, became a planet with oceans and air and eventually us. That is part of why scientists care so much about objects like this. They are time capsules. They carry, locked inside them, the chemistry and the structure of the early solar system, frozen in place for billions of years. To study an asteroid is, in a real way, to read a page from a book that was written before the Earth had finished forming. For most of those billions of years, Apophis would have lived a quiet and anonymous life, drifting along an orbit that posed no threat to anyone and attracted no attention, because there was no one to pay attention. But the orbits of asteroids are not permanent. They are nudged and reshaped over enormous spans of time by the gravity of the planets, by collisions, and by forces so subtle they took us centuries to even imagine. At some point, through one of these slow processes, Apophis was eased onto a new kind of path, one that brought it across the orbit of the Earth. It became what we call a near-Earth asteroid, a member of the population of objects whose orbits intersect or come close to our own. There are many thousands of these, and astronomers spend a great deal of effort hunting for them and tracking them, precisely because a few of them, over long enough spans of time, could one day pose a genuine danger. Apophis is in a group called the Atens, asteroids whose orbits are, on average, slightly smaller than the Earth's, so that they spend most of their time a little closer to the Sun than we do, swinging out to cross our path only at certain points. As it happens, the encounter in 2029 will actually change that. The pull of the Earth will reshape its orbit enough to enlarge it, and afterward Apophis will be reclassified into a different group entirely. The flyby will not only let us study the rock. It will physically rewrite the path it has followed for ages. Now we arrive at the night it entered our awareness. The story of Apophis as a thing humans know about begins on a desert mountaintop in Arizona, on the 19th of June in 2004. That date matters more than it might seem, and I will circle back to why before the night is out. At Kitt Peak National Observatory, 3 astronomers, Roy Tucker, David Thalin, and Fabrizio Bernardi, picked out a faint moving dot in their data. A new near-Earth asteroid, one of hundreds discovered every year. There was nothing in that first sighting to mark it as special. It was simply another point of light, catalogued and passed along for follow-up observations like all the others before it. Nobody that night had any idea that this particular dot would, within a matter of months, become the most famous and the most feared asteroid on Earth. The name came later, and the story behind it is more lighthearted than you might expect for an object that would briefly terrify the planet. When a newly discovered asteroid has its orbit confirmed, the people who found it earn the right to suggest a name. And the team who found this one happened to be fans of a science fiction television series, one in which the chief villain, a parasitic alien who posed as a god, was named after the ancient Egyptian serpent. So the name arrived first as a wink, a nod to a fictional bad guy. It was only afterward, as the object's true nature began to reveal itself, that everyone realized how unnervingly well the older, deeper meaning fit. Because the original Apophis of Egyptian myth was not just any figure. It was the serpent that waited in the dark to swallow the world. We had taken a rock that, for a brief and frightening window, genuinely seemed as though it might strike the Earth, and we had given it the name of the very thing the ancient world believed was always trying to end everything. The name began as half a joke. The numbers that came next turned it into something that felt, for a few days, uncomfortably like a prophecy. Because Apophis did not stay quiet for long. As more observations trickled in during the closing months of 2004, the people whose job it is to calculate the orbits of these objects began to see something they very much do not like to see. The projected path of this asteroid, traced years into the future, kept passing closer and closer to the Earth. And the early measurements carried enough uncertainty that the word impact stopped being merely theoretical and started being a real, calculable possibility. By the final days of December, in the quiet stretch around Christmas, the calculated probability that Apophis would strike the Earth on its 2029 approach had climbed to about 2.7%. I want you to sit with that figure for a moment because 2.7% might not sound like very much. It is fewer than 3 chances in 100. But this was not a coin flip or a weather forecast. This was the estimated probability that a rock several hundred meters across would hit the planet you are standing on a date that could already be circled on a calendar. Imagine being told there is roughly a 1 in 37 chance that an object large enough to devastate a region or raise a wave across an ocean will arrive on a specific Friday a couple of decades away. That is the kind of number that makes serious, careful people go very quiet. Astronomers have a way of communicating exactly this kind of threat to the public, a scale called the Torino scale. It runs from 0, meaning no concern whatsoever, up to 10, meaning a certain collision capable of global catastrophe. Most asteroids that ever get a rating sit at 0 or 1, and almost all of them quietly fall back to 0 as more observations come in and the orbit is refined. The scale is designed so that climbing it is difficult and falling off it is the normal, expected outcome. Apophis did not quietly fall. It climbed. For a short window around the end of 2004, it reached a level 4 on that scale, defined as a close encounter meriting the attention of astronomers, with a real, if still small, chance of a regional disaster. No object had ever been rated that high before. And in all the years since, none has matched it. For those few days, the most dangerous object humanity had ever catalogued carried the name of the god of chaos and a date already fixed on the calendar. Now, this is important, so let me be careful and honest about it. The way this unfolded was the opposite of a cover-up. The rising probability through late December was tracked openly, with astronomers around the world trading urgent messages and refining their numbers in real time. When the all-clear eventually came, it too was announced openly in the scientific literature and in the press. Every step of this story, the climbing odds, the worry, the patient years of additional tracking, and finally the measurements that closed the case, happened in the open. I'm going to ask you to hold on to that fact because later in the night, when we get to the wilder theories that circulate about this object, you are going to encounter the claim that the truth about Apophis is being hidden from you. And the entire documented history of this rock, every public conference and published paper, says the precise opposite. The strangeness of Apophis is not a secret. The strangeness of Apophis is the headline of the research. It got more complicated before it got simpler, and the complication is worth understanding because it shows just how careful these calculations have to be. Even after the chance of an actual collision in 2029 was ruled out, a subtler danger lingered. There was a possibility that during the 2029 pass, Apophis might fly through a very specific and very small region of space that scientists call a keyhole. A keyhole is a kind of gravitational trap, and it is one of the most counterintuitive ideas in all of orbital mechanics, so let me give you a way to picture it. Imagine you are sitting high in the stands of an enormous stadium and far below, somewhere in the vast field, there is a single small open hatch in the ground, perhaps a meter across. And imagine that if, and only if, a ball rolling across that field happens to drop through that one specific hatch, it gets routed through a hidden tunnel that delivers it, much later, to a destination you very much do not want it to reach. Miss the hatch by even a little, and the ball simply rolls on harmlessly across the grass and nothing bad happens. A gravitational keyhole works in much the same way. It is a tiny patch of space, in this case estimated at less than a kilometer across, and only if Apophis passed through that exact patch in 2029 would the Earth's gravity bend its path by precisely the amount needed to line it up for a collision on a later trip around the Sun everywhere else, and the patch is surrounded by an almost incomprehensibly large everywhere else. The asteroid sails on and the future stays safe. For a few years, that keyhole kept Apophis on the watch lists, because the worry was no longer simply whether it would miss us in 2029. The worry became whether it would miss us cleanly, or whether it would thread that one small doorway that would send it back to strike us 7 years later, in 2036, on what would happen to be Easter Sunday. It is a genuinely unsettling idea, that a body could miss you by a wide and comfortable margin and yet pass through an invisible point that quietly seals your fate decades down the line. But this is also exactly where the system worked the way it is supposed to. The astronomers did not panic. They kept watching. They gathered more data, refined the orbit, and narrowed the uncertainties year after year. And in March of 2021, using the enormous radar dish at the Goldstone complex in California along with other observatories, they pinned down the path with such precision that they were able to do something both rare and deeply reassuring. They cleared it completely. The radar data ruled out any chance of impact from Apophis for at least the next 100 years. The odds of the once-feared 2036 strike collapsed to essentially nothing. The keyhole worry was retired. The serpent, for the foreseeable future, has no path to us. That certainty was not the work of a single night or a single clever calculation. It was earned slowly across 2 decades of patient watching, and the patience itself is part of why we can trust the result. Tracking an asteroid is not as simple as pointing a telescope and writing down a number. Some years, Apophis swung around to a part of its orbit where it appeared too close to the Sun in our sky to be observed at all, and for long stretches it simply vanished from view, waiting for the geometry to come back around. So astronomers seized every window they could. In 2013, the asteroid made a much more distant pass, still nearly 17 million kilometers away, nothing like the brush coming in 2029, and the Great Radar Dish at Goldstone, working in coordination with another enormous instrument in West Virginia, tracked it for about 2 weeks around its closest point. By having one dish transmit while the other listened, they effectively doubled the strength of the returning signal, and from that they pinned down the asteroid's distance to within a margin of just a few hundred feet across all those millions of kilometers. Each of these campaigns, the optical observations stretching back to that first night in Arizona, the radar passes in 2013 and again in 2021, added another layer of precision, narrowing the uncertainty in the 2029 approach from hundreds of kilometers down to just a few. This is what real certainty looks like in this field. Not a single dramatic announcement, but the slow, unglamorous accumulation of measurement upon measurement, until the path of a wandering rock decades into the future is known better than almost anything else of its kind in the sky. That precision did not come easily, and to achieve it the astronomers had to account for a force so subtle that most people have never even heard its name. It is called the Yarkovsky effect, and it turns out to matter for our story in more ways than one, so it is worth understanding. The idea is this. An asteroid sitting in sunlight absorbs heat on its daytime side. Then, as it rotates, it carries that warmed patch around and radiates the heat away into space a little later, in a slightly different direction. And radiating heat, strange as it sounds, produces a tiny push, like the faintest imaginable exhaust from the surface. On its own, in any single moment, this push is almost nothing. But over years and decades and centuries, that whisper of a force can nudge an asteroid's orbit by a meaningful amount. For Apophis, measuring the Yarkovsky push was essential to nailing down whether it would thread the keyhole, and astronomers found that the object was drifting from its predicted position by a small but detectable amount each year. But here is the quiet beauty of it. How strongly that push acts on a body depends on how the body holds and releases heat, which in turn depends on what its surface and its interior are made of. So the very measurement that helped clear Apophis of any future impact was also one of the first hints that this might be a loose, porous, low-density object rather than a solid mountain of stone. The reassurance and the mystery came out of the very same data. So here we are, with one of the strangest gaps in all of planetary science. We are masters of the orbit and strangers to the object. Think about how lopsided that is. We can tell you to the kilometer where a 340-meter rock will be on a specific Friday evening 4 years from now, after it has traveled hundreds of millions of kilometers around the sun. The position of Apophis in 2029 is known better than the position of almost anything else of its kind in the entire solar system. And yet, if you ask a far simpler and more childlike question, what is it actually made of, how strong is it, what is hiding just beneath its surface, the honest answer is that we mostly do not know. We have measured the dance with breathtaking accuracy. We have barely seen the dancer. That gap makes a certain kind of sense once you understand how we study these objects. An orbit reveals itself over time. You watch the asteroid, you record its position, you watch again, you record again, and slowly, position by position over years, the path becomes undeniable. The orbit is patient. It gives itself up to anyone willing to keep looking. But the interior of an asteroid reveals nothing on its own. It just sits there, dark and silent, hundreds of millions of kilometers away, surrendering almost no clue about what lies within. You cannot see inside a solid object that far away no matter how powerful your telescope. The inside is a closed door, and until very recently, nothing was ever going to open it because nothing was ever going to disturb Apophis. And that is precisely the imbalance that makes everything else about this story possible. Because we are so certain of where the asteroid will be, we can aim spacecraft at it and plan observations down to the second. We can turn the 2029 pass into the single most anticipated natural experiment in the history of the field. The one thing we cannot predict, the thing nobody can predict, is what that experiment will reveal about the part of Apophis we have never been allowed to see. And the first real clue that the inside might be strange came not from any spacecraft, but from the simple, stubborn fact that when we finally got a decent look at the shape of this rock, it looked like something it had very little business looking like. When the radar data from 2021 came back, the astronomers received more than just a refined orbit. They received a picture. A rough, grainy, hard-won picture of the actual shape of Apophis, the first time we had ever really glimpsed the silhouette of this thing rather than just a moving dot. And the shape that emerged was not the simple round potato or lumpy boulder that most people picture when they hear the word asteroid. It appeared to be elongated, stretched out along one axis, and there were strong hints that it might be divided, perhaps pinched in the middle, with the suggestion of two distinct lobes joined at a narrower waist. The descriptions that came back reached again and again for the same comparisons. It looks a little like a peanut, like a dumbbell, like two rocks resting against one another. I have to be careful here because the exact shape of Apophis is still genuinely uncertain, and that uncertainty is part of the whole point. The radar images we have are crude, more like a smudged shadow than a photograph. What they suggest is that Apophis may be elongated, and possibly what astronomers call a contact binary, though that is something the upcoming missions are partly going there to settle. But even the possibility is significant because a shape like that, two lobes leaning against each other, has a name and a meaning in the world of asteroids. A contact binary is exactly what it sounds like. Instead of one object, you effectively have two separate bodies that long ago drifted together, touched and stayed touching, held against each other by the faint pull of their own mutual gravity. They are not fused. They are not welded into a single solid stone. They are leaning on one another, joined at a seam, like two boulders that rolled into each other in the dark and never rolled apart. How does something like that even come to exist? There are a few ways, and they all tell you something a little unsettling about how loosely the small bodies of our solar system are actually held together. In some cases, two separate asteroids drifting on similar orbits came together so gently, at speeds of perhaps a few centimeters per second, walking pace or slower, that instead of shattering one another they simply stuck. In other cases, a single loosely packed body was spun faster and faster by sunlight, through a cousin of that same Yarkovsky effect, until it stretched, partially split, and then settled back into a two-lobed shape. Either way, the lesson is identical. These objects are not solid sculptures carved from a single block of stone. They are assemblages. Things that came together piece by piece, and that are held in their current shape by almost nothing at all. And once you learn to look for this kind of shape, you start to see it everywhere we have sent a spacecraft. There is a small asteroid called Itokawa, which a Japanese mission visited and which turned out to look very much like a sea otter or a peanut, clearly made of two pieces resting together. When a European mission arrived at a comet known by the catalog number 67P, it found not a single dirty snowball but two great lobes joined by a neck, shaped a little like a rubber duck, and that neck became one of the most studied features of the entire mission because scientists could see stress fractures running through it. And out at the very frontier of the solar system, when a NASA spacecraft flew past a distant frozen object nicknamed Arrokoth, it photographed the most perfect contact binary we have ever seen up close. Two nearly round lobes pressed gently together, like a snowman built at the edge of the dark. We have a whole gallery of these things now, and the pattern that runs through all of them is the join, the waist, the neck, the place where two became one and never quite finished the merger. So if Apophis really does have that shape, it would not be an oddity. It would be a member of a family we are coming to know well, and that is exactly what makes the prediction for 2029 something we can take seriously. We would not be guessing about an unprecedented object. We would be looking at a familiar kind of body, with a familiar weak point, and asking what a familiar kind of stress will do to it. That neck, if it exists, is the detail that turns a piece of trivia into the heart of the story, and I want to tell you why. In a body made of two lobes, the neck is the seam. It is the narrowest part, the join, the place where the two halves meet. And anywhere there is a join, there is a weakness. Think of any object you have ever held that was made of two pieces stuck together. Where does it break if it breaks? Almost never through the solid middle of either piece. It breaks at the seam. The neck of an asteroid like this is its seam, and a seam is exactly the kind of feature that becomes interesting the moment something begins to pull the two halves in different directions. Hold that thought because we will need it. The single most fragile line through the entire structure is precisely the place that the Earth's gravity is going to pull on the hardest in 2029. The shape is not just a curiosity. If it is what we suspect, it is a map of where the experiment will press. The shape, though, is only half of the strangeness. Because when we look not just at the outline of Apophis but at how heavy it appears to be for its size, and at the genuinely bizarre way it moves through space, the picture got stranger still, and it began to suggest that this may not really be a solid rock at all. So here is a question that sounds simple and turns out to be one of the most important you can ask about any asteroid. How heavy is it for its size? Not how big, not how massive in absolute terms, but how tightly packed. Because the density of an object, how much matter it crams into a given volume, tells you what it is likely made of, and crucially how it holds itself together. The best estimates for Apophis suggest a density that is, frankly, low. Lower than you would expect for solid stone. The kind of solid rock you would find in a mountain on Earth is quite dense, but a body like Apophis appears to be considerably less so, and there is really only one good way to explain a number like that. Apophis probably cannot be solid all the way through. If it were a single intact boulder of stone, it would weigh more than it seems to. The only way to get a body that large to be that light is for it to be full of empty space, riddled with gaps and voids and pockets of nothing. This is what scientists mean when they reach for a phrase you may have heard, a rubble-pile. The picture is not a single smooth mountain hurtling through the dark. The picture is a slowly drifting heap of gravel and boulders and dust, thousands upon thousands of separate pieces ranging from grains of sand to chunks the size of houses, held together not by any glue, not by any solid chemical bonds, but almost entirely by their own faint mutual gravity. A rubble-pile asteroid is less like a stone and more like a pile of sand that is just barely holding its shape in the gentlest possible grip. In principle, on a body that's small, with gravity that weak, you could press your hand into the surface. The whole thing is held together by a force so feeble that a strong enough tug from the outside could rearrange it. And we are not merely guessing at this in the abstract because we have visited objects exactly like this and seen them up close. When the Japanese spacecraft reached Itokawa, it found precisely this. A rubble pile, a jumble of boulders and gravel with almost no solid core, so loosely bound that it was barely an object at all. And when a NASA mission visited an asteroid called Bennu and reached down to grab a sample of its surface, the surface behaved in a way that genuinely startled the team. The spacecraft sank in as though the ground were a pit of loose plastic balls, and the scientists later said that if it had not immediately fired its thrusters to back away, it might have kept sinking. These objects are not what our imaginations tell us asteroids are. Many of them are flying rubble. Where does a rubble pile come from? The leading idea is almost violent in its simplicity. Long ago there was a larger, more solid parent body, and at some point it was smashed, shattered in a collision with another object into countless fragments. But the fragments did not all fly apart forever. The combined gravity of the debris, weak as it was, slowly drew a portion of it back together over thousands of years. And what reassembled was no longer a solid rock. It was a heap, a gravitational clump of pieces, with all the gaps and voids and loose contacts you would expect from a pile that was poured rather than carved. In this picture, Apophis is the reassembled ghost of something that was broken long ago. The empty space inside it is the memory of that shattering, the gaps between fragments that never closed. And the force holding it together is shockingly weak. We are not talking about the bonds that hold a boulder together. We are talking mostly about gravity, plus a faint stickiness between grains, the same subtle surface attraction that makes flour clump or lets fine dust cling to a surface. For a body the size of Apophis, that adds up to a grip you can measure but only just. This is exactly why the encounter in 2029 is such a live and genuinely open question. You are taking an object that may be held together by little more than a whisper, and you are exposing it to the pull of an entire planet. With a solid rock, you would not even ask the question. The rock would simply pass by unchanged and we would learn nothing new from the geometry of it. But with a rubble pile, the question is wide open, and that is what makes the suspense real rather than manufactured. And there is one more strange behavior that fits this picture perfectly, and that is the way Apophis moves. Most objects in space, left alone for long enough, settle into a simple, stable rotation. They spin smoothly around a single axis, the way a well-thrown football spirals through the air, or the way a planet turns on its pole. Internal friction, the tiny flexing and rubbing inside a body as it wobbles, slowly bleeds away any unevenness over time and leaves a clean, repeating spin. Apophis does not do that. Apophis tumbles. It is in what physicists call a non-principal axis rotation, a state in which the object is essentially rotating around more than one axis at the same time, so that it rolls and wobbles as it spins, never quite settling, never repeating cleanly. There is one stronger rhythm in its tumble that takes around 30 hours, and layered on top of it a second, slower wobble. Picture a football thrown by someone who has no idea what they are doing, going end over end and sideways at once, never finding a clean spiral. That, more or less, is how this object moves through the dark. A tumble like that is not just motion. It is a record. For a body to still be tumbling after billions of years, one of two things has to be true. Either something disturbed it relatively recently, or its internal structure is so unusual that the wobble has never managed to damp out over the entire age of the solar system. Both possibilities point straight back at the interior because the way a body distributes its mass, what physicists call its moment of inertia, completely governs how it tumbles. Make one lobe denser than the other, hollow out a region here, pack it tight there, and the tumble responds. So a measured tumble that refuses to match the simplest model is not a paradox, and it is not a sign of anything mysterious or otherworldly. It is the interior speaking. It is, in fact, one of the only voices the inside of Apophis has, and it has been quietly speaking the whole time, if only we knew how to listen closely enough. I should pause here and deal honestly with something because there is a great deal of conversation about this object online, and some of it seizes on exactly these features, the suspicious shape and the strange tumble, and runs much further with them than the evidence allows. There are threads that circulate, full of confidence-specific numbers, claiming that the way Apophis spins proves that something inside it is flexing and shifting, or that the body is on the verge of coming apart. And I want to be fair to the instinct behind that because the instinct is not foolish. A body that may be two lobes joined by a thin neck really is a more fragile thing than a single solid boulder. A tumble really does carry information about an uneven interior. The people noticing these features are noticing something true. But the drama that gets wrapped around them, the precise ratios and the breathless certainty, tends to run well ahead of what we can actually verify. The honest version is more modest and, I think, more interesting. The shape and the spin and the low density all point in the same direction, toward a loosely bound, uneven, lumpy object whose interior we cannot yet see. They do not point toward catastrophe. They point toward a question. And the wonderful thing is that the question is about to be answered not by argument but by the Earth itself. Because here is what is really going to happen on that Friday evening, underneath the beautiful, silent light show in the sky. As Apophis falls past the Earth, our planet's gravity is going to reach up and take hold of it. Not gently and not merely symbolically. The same force that holds you in your chair and pulls the tide up the beach is going to grip a several hundred-meter asteroid and stretch it and squeeze it in a way it has not been touched in possibly millions of years. To understand what that means, you need to understand a force you already know intimately, even if you have never named it. It is the same force that raises the ocean into a bulge twice a day and lets it fall again. It is the force that long ago locked the moon so that it shows us only one face. It is called the tidal force, and it is not really a separate force at all. It is simply gravity behaving unevenly. Gravity gets weaker with distance. So when a large body like the Earth pulls on an extended object like an asteroid, the side of that object facing the Earth gets pulled a little harder than the side facing away, simply because the near side is closer. The whole object feels a stretch, a difference in pull from one end to the other. On the ocean, that difference lifts the tides a few meters. On a loosely bound rubble pile passing barely 30,000 kilometers overhead, that same uneven pull becomes something far more interesting. As Apophis comes in, it enters the region where the Earth's gravity is not only strong but, more importantly, steeply changing. The side facing us feels a noticeably stronger tug than the far side. The body is stretched along the line pointing at the Earth. And because it is tumbling, different parts of it swing into and out of that line of maximum stress over and over during the hours of closest approach. The Earth does not simply pull on Apophis once. It works it like a pair of hands kneading a lump of dough, twisting and stretching and releasing as the asteroid rolls past. For a body held together by the faintest of grips, this is the most violent thing that has happened to it in a very, very long time. Now, there is a crucial line in space that decides whether this kind of squeezing tears a body apart or merely disturbs it, and I want to introduce it because it is the single best reason not to worry, and at the same time the reason the question stays genuinely open. It is called the Roche limit. The Roche limit is the distance from a planet inside which the tidal stretching becomes so strong that a body held together only by its own gravity would be pulled apart. Cross that line, and a strengthless rubble pile cannot hold itself together. Stay outside it and it can. For the Earth, and for a low-density body like Apophis, that limit sits somewhere around 18,000 kilometers from the planet's center. And here is the number that matters more than any other in this entire story. Apophis, at its closest, will pass roughly 38,000 kilometers from the center of the Earth. That is comfortably outside the Roche limit. It is not even close to the line where pure gravity would lose its grip. This is the fundamental reason the models do not predict that Apophis simply disintegrates. It is passing through the zone where it gets stressed and disturbed, not the zone where it gets dismantled. So why is there any suspense at all if it stays safely outside that line? Because the Roche limit describes the threshold for total disruption of a body held together by gravity alone, and reality is messier than that clean cutoff. Real rubble piles have a little extra cohesion, that faint stickiness between grains which helps them resist. But they also have weak points like the neck we discussed, where the local strength can be far lower than the average across the whole body. The Roche limit tells you that Apophis will not be torn to pieces. It does not tell you whether a lobe will shift, whether the surface will avalanche, whether the spin will be wrenched onto a new rate, or whether a weaker seam will give just a little. Those outcomes live in the messy middle ground between nothing happening and total destruction. And that messy middle is exactly where the interior we cannot see gets to cast the deciding vote. This is where the modeling becomes its own kind of careful art. To predict what happens, scientists cannot simply plug a single object into an equation. They have to build it virtually out of its pieces. The most detailed simulations construct a model of Apophis from thousands of individual particles, each one standing in for a chunk of the rubble pile, and then they let those particles interact with one another and with the Earth's gravity through the entire encounter, contact by contact, nudge by nudge. And they run it many times over, changing the assumptions each time. What if the two lobes have the same density? What if one is much denser than the other? What if the cohesion holding the pile together is a little higher or a little lower? Each run is a slightly different possible Apophis, and each one responds to the flyby in its own way. The spread of those responses is the range of possible futures, and it is the honest reason that no single confident answer can be promised. The models cannot tell us what will happen. They can only lay out the menu of what could. Let me walk you slowly through the hours of the encounter itself, because it is not an instant. It is a slow, building event that plays out across most of a day, and feeling the shape of it is part of feeling the suspense the way the scientists do. In the hours before the closest approach, Apophis is still far enough out that the Earth's pull is gentle and nearly even across its body. It is tumbling along as it has for ages, undisturbed, and the spacecraft that will be riding with it are taking their careful baseline measurements, recording the spin, the shape, the surface, the exact starting state of the rock. This is the calm before. Then, as the asteroid sweeps inward, the difference in pull between its near side and its far side grows. Slowly at first, then faster, the stretching force climbing as the distance shrinks. The body that has been left alone for so long begins, for the first time in perhaps millions of years, to feel itself being pulled unevenly. At the moment of closest approach, that evening high above the Atlantic, the stress reaches its peak. This is the instant everything has been building toward, the few minutes when the Earth's grip is tightest and the stretching is strongest. If the neck is going to relieve its compression and let a lobe roll, this is when. If the surface is going to slide, this is when the slow avalanches begin. If the spin is going to be wrenched onto a new rate, this is the wrench. And then, almost as quickly as it peaked, it begins to ease. Apophis is moving fast and it does not linger. Within hours, it is already receding, the stress falling away as quickly as it rose, and the asteroid is left to settle into whatever new state the encounter has given it. The whole transformative event, the only one of its kind we will ever have a front row seat to, is essentially over in an afternoon. And here is the single measurement that everything comes down to: the spin. Before the encounter, we measure exactly how Apophis tumbles, its rate, its axis, its wobble, in as much detail as we possibly can. After the encounter, we measure it all again. The difference between those two measurements is the readout of the experiment. It is the answer the asteroid gives. If the spin has barely changed, that tells us the interior is relatively strong, well-bound, resistant, more like a coherent body than a loose heap. If the spin has changed dramatically, if the rate has noticeably sped up or slowed down, and the axis has swung to point somewhere new, that tells us the interior is weak, loose, easily moved, a true rubble pile that the Earth was able to grab and reshape. The spin is the voice of the interior, and the encounter is the moment we finally get to hear it speak clearly because we are the ones who provoked it. Picture the two extremes so you can feel what is actually at stake in that measurement. In the gentle version, the spacecraft watch Apophis pass through the encounter almost serenely. The spin shifts a little, a few small landslides perhaps stir the surface, and the asteroid comes out the other side looking much as it went in. We learn that it is stronger than its low density had suggested, and that itself is a valuable surprise. In the more dramatic version, the spacecraft watched the asteroids tumble visibly change over the hours, watch fresh material slide and expose brighter, unweathered ground beneath the darkened skin, watch one lobe subtly reposition against the other at the neck, and they record a body that has been measurably reshaped by its encounter with our world. We learn that these objects are even more fragile and more alive than we thought. Both outcomes are scientific gold. Both rewrite a piece of what we know. And which one we get is a question only Apophis can answer. In the single afternoon it has to answer it. Within that range, the mechanism that most excites the scientists is the surface response, because that is the part we have the best chance of actually seeing with our own instruments. On a body with gravity, this weak, loose material is barely held down to begin with. When the spin rate changes, even slightly, and the tidal stress ripples through the body, the delicate balance that keeps grains and pebbles and boulders in place can tip. Material can begin to slide, to creep downslope, to avalanche in slow motion across the surface. Scientists call this resurfacing, and it matters far more than it might sound because of what lies just underneath. The outer skin of any asteroid is slowly altered over millions of years by the constant bombardment of solar radiation and tiny micrometeorites, a process called space weathering that darkens and changes the surface. The material just below that skin is pristine, unaltered, a sample of what the asteroid is really made of. If the 2029 encounter triggers landslides that strip away the weathered skin and expose fresh material beneath, then for the first time we would get to see the true, unweathered face of a near-Earth asteroid, revealed not by a drill or a sample but by the hand of our own planet. There are even hints that this could change how the asteroid registers to our instruments, shifting it from looking like a weathered object to looking like a fresh one, simply because the Earth shook its surface awake. I want to be careful and honest here because this is exactly the kind of moment where excitement tends to outrun the evidence. The actual physical deformation of the body, the squashing and stretching of its overall shape, is predicted by most models to be tiny. We are talking about movement on the scale of centimeters, sometimes less. And much of that deformation is expected to be elastic, which means it springs back the way a stress ball returns to its shape after you stop squeezing it. By the mainstream prediction, Apophis is not going to be visibly crushed or bent. If you were floating beside it, you would not see it deform like clay. The changes to its surface and its shape are subtle. So let me say it as plainly as I can. The most likely outcome of this encounter is not destruction. It is a measurable change in spin and a set of small, subtle disturbances. But those disturbances are not spread evenly across the body. When the models look at where the stress concentrates during the flyby, the answer comes back the same way nearly every time. The stress piles up at the neck if there is one. The waist between the two lobes is where the tidal forces do their most focused work, where the pull is most likely to loosen the compression that normally holds the two halves snugly together. And in some of the models, that relief is just enough to allow a real, if subtle, shift. A slight rolling or repositioning of one lobe against the other, as the grip that held them locked is briefly loosened by the Earth. I know that the modelers describe these effects with restrained words. Small, limited, possibly negligible. And on the scale of a Hollywood disaster, yes, this is modest. There is no explosion. There is no shattering. But I want you to step back for a moment and feel the actual weight of what I just described, because the restraint of the language hides something genuinely historic. We are talking about watching a planet reach out and change the spin of an asteroid, tilt the direction of its rotation, loosen the seam between its two halves, and possibly trigger landslides that expose material no light has touched in ages, all in real time, all in a single pass. We have never seen anything like this happen. Not once in the entire history of human science have we had a front-row seat to a planet physically reworking another world. Modest on the cosmic scale is still completely unprecedented on the human one. And now we arrive at the louder, wilder version of this story, the one that circulates most furiously online, and I would be doing you a disservice if I did not take it seriously and walk through it carefully, because it deserves a fair hearing before we test it against the science. The dramatic version goes like this. Apophis, the believers say, is two lobes joined by a thin neck. That neck has some critical width, some threshold of thickness. Above that width, the neck is strong enough to survive the tidal stress of the flyby and hold the body together. But below it, if the neck is thinner than the threshold, the stretching force of the Earth could overwhelm it and the neck could fail. The two lobes could separate. And then, the theory continues, things get truly strange because the moment Apophis stops being one object and becomes two, the two pieces no longer follow the same path. They have slightly different shapes, slightly different masses, and they would drift apart onto slightly different orbits. And the most provocative claim of all is this. One of those separated pieces might thread its way through one of those gravitational keyholes, the narrow doorways to a future impact that the combined body had already been measured to sail safely past. I want to give that scenario its due because it is not built on nonsense. The instinct behind it is grounded in real physics. Next really are stress concentrators. That is true in engineering, in bones, in welds, in a chocolate bar you snap in half. The thinnest part of a joined structure really is where failure tends to begin. And contact binary asteroids really can come apart under tidal stress. We have good reason to believe that some of the asteroid pairs we observe, two separate rocks traveling on nearly identical orbits, were born from a single parent that came apart in exactly this way during a close planetary encounter in the distant past. So the idea that a close past could stress a fragile rubble pile at its weakest point, and that in principle such a body could be pulled apart, is not a fantasy. It is a real category of event that genuinely happens in our solar system. The people pushing this idea are not inventing the mechanism. They are taking a real mechanism and turning the dial all the way to the maximum. And here is where it runs too far. There really is a kernel of sound physics in the idea of a critical neck width. The strength of a neck, its ability to resist being pulled apart, does scale with how much material spans it, roughly with the area of its cross-section. A thicker neck has more grains in contact, more gravity pulling the lobes together, more cohesion across the joint, and so it can resist more stress. A thinner neck has less of everything and gives way more easily. So the concept that there is some width below which a given tidal stress wins is not nonsense. The problem is the confidence in the specific number. We do not actually know the width of Apophis's neck, if it even has one, with anything like the precision needed to say it sits on one side of a sharp line. And we do not know its cohesion. And the threshold itself depends entirely on assumptions about both. A real principle has been turned into a precise-sounding cutoff that the data simply does not support. That is the difference between a scientist and a viral thread. The scientist names the uncertainty out loud. The thread quietly sands it away until the number looks like fact. And here is something the dramatic version almost never mentions, which deflates it considerably even if you grant the breakup entirely. If Apophis somehow did separate at the neck, it would not happen like an explosion. There would be no blast, no scattering of shrapnel. The two lobes, having been held together by the faintest of grips, would simply drift apart at a speed of maybe a few centimeters per second at the absolute most, more likely far slower. They would separate the way two boats drift apart on a still lake when you stop holding them together. The pieces would continue along almost exactly the same orbit, side by side, parting by mere meters over the course of hours. For one of those gently drifting pieces to then thread a gravitational keyhole less than a kilometer wide, a keyhole the combined body was already measured to miss by a wide and comfortable margin, the separation would have to nudge it by just the right amount, in just the right direction. That is an astronomically specific coincidence, stacked on top of an event the models already say will not occur. You can see how a chain of unlikely things, each one multiplied by the next, drives the real probability down toward the vanishing point. The scenario is not impossible in the way a square circle is impossible. It is improbable in the way that flipping a coin and having it land balanced on its edge twice in a row is improbable. So the honest verdict on the breakup story is not a flat, dismissive no. It is a grounded, quantified, very unlikely, and here is exactly why. The detailed modeling, the same simulations built particle by particle to represent a rubble pile, do not predict that Apophis breaks apart. They predict, overwhelmingly, that the deformation is on the scale of centimeters, and that it is largely elastic, a flex and a settling rather than a rupture. The stress concentrates at the neck, yes, and the neck may shift and the lobes may roll slightly against each other. But a clean separation into two free pieces is not what the physics says happens at this distance, with this geometry for a body of this size, well outside the Roche limit. The Earth's pull at 30,000 kilometers is firm, but it is not the kind of grip that tears a several hundred-meter body in half. The breakup is the far, unlikely tail of the range of possibilities, not the center of it. And the keyhole twist sits on top of a breakup the models do not expect in the first place, which makes it a small possibility resting on an unlikely one. There is a memory that hangs over all of this, and it is worth invoking because it is the closest thing we have ever actually seen to the dramatic scenario, and it is also the perfect illustration of why Apophis is not it. In 1994, a comet called Shoemaker-Levy 9 did exactly what the believers fear Apophis might do. It passed too close to Jupiter, and Jupiter's enormous tidal forces tore it apart, ripping the comet into a string of more than 20 fragments that astronomers described as a string of pearls strung across the sky. The comet had, in fact, already been torn apart on an earlier close pass before anyone even discovered it. By the time astronomers found it, it was already a broken thing, a glittering row of icy chunks marching above in the dark, each one trailing its own faint haze. For more than a year, the whole world knew those pieces would have fallen to Jupiter. And on a series of days in July of 1994, they did, one after another, slamming into the giant planet at tremendous speed, each impact blowing up a dark plume of debris. Some of the bruises they left in Jupiter's clouds were larger than the entire Earth, and they lingered for months, visible in backyard telescopes. That week changed how our species thinks about the sky. It was the first time we had ever predicted a collision between two bodies in the solar system and then watched it unfold on schedule. It proved, in front of everyone, that these impacts are not ancient history frozen in old craters, but a process that is still happening, still shaping worlds right now. It is a large part of the reason the funding and the will to hunt for dangerous asteroids gathered real momentum in the years that followed. The string of pearls is burned into the memory of everyone who studies these objects, and it is exactly the image that flickers in the back of the mind when someone says the words tidal forces and two-lobed asteroid in the same breath. So when the online theories reach for that picture and apply it to Apophis, I understand the instinct completely. It is the most spectacular thing tidal forces have ever done in front of us. But the memory has to be matched to the reality. Shoemaker-Levy 9 was a fragile comet that got captured by the most powerful gravity well among all the planets and was shredded over repeated close passes. Jupiter is a monster, more than 300 times the mass of the Earth, with a tidal grip our planet cannot begin to match. That comet did not just pass Jupiter. It was captured, dragged in on a tightening loop, and torn apart over time. Apophis is a stony rubble pile making a single swift pass by a far smaller world, outside the line where pure tides could dismantle it, and then continuing on its way. The Earth is not Jupiter, and a brush is not a plunge. The string of pearls is a haunting and a real warning about what is possible at the extreme. It is not a forecast for this encounter. So the mature way to hold all of this, the honest way, is not to expect catastrophe, and it is not to dismiss the question either. It is to sit in the suspense. The drama of Apophis is not that it will break apart. It almost certainly will not. The drama is that we genuinely have to wait and watch to find out what it does, because the only instrument precise enough to settle the argument is the encounter itself. And there is one more layer of honesty I owe you, the one genuine science-based source of lingering uncertainty that gets lost between the people who shout that we are doomed and the people who wave the whole thing away. Every reassuring word I have said rests on the models, and the models rest on assumptions about the interior, the very thing we have admitted we cannot yet see. When a scientist says breakup is not expected, what they honestly mean is that breakup is not expected if the interior is roughly as strong as we think it probably is. We do not know for certain that it is. And on top of that, there is a subtle point about the orbit. Apophis is going to be very difficult to observe from Earth for several years leading up to the encounter, vanishing into the glare near the Sun until it re-emerges closer to the event. During that window, in principle, the asteroid could pass close to some other small object we have not yet detected, and that encounter could give Apophis the faintest gravitational nudge. The effect would be minuscule, and it does not resurrect the impact scenario. But it is a reminder that every confident statement about exactly where Apophis will be, and therefore exactly how hard the Earth will squeeze it, rests on the assumption that we have accounted for everything out there. We almost certainly have. But almost is not the same as certainly, and good scientists are careful to say so. That is not fear-mongering. That is the honest texture of a real prediction about a real object in a crowded solar system. Stack it all together, and you can finally see why the mood among the people who study this is what it is. We have a body whose interior is unknown, passing outside the line of certain destruction but well inside the range where strange and subtle things can happen, with a possible weak point that the encounter will stress hardest, and a small but real residual uncertainty riding on top of everything. None of that adds up to disaster. All of it adds up to suspense. The scientists are not bracing for a catastrophe. They are bracing for a surprise, which in a field built on prediction, is its own peculiar and uncomfortable thrill. They have set up the most elaborate observation of a single rock in the history of their discipline, and they are waiting to find out whether the object confirms what they think they know or astonishes them. Which brings us to the most practical question of the entire night. When that one and only experiment runs, who exactly is going to be watching and how closely? Because the answer is the difference between learning almost everything and learning almost nothing. For most of the close encounters in the long history of the solar system, no one was watching. Asteroids have been swinging past planets and being reshaped by their gravity for billions of years, and every single one of those events happened in the dark, unrecorded and unmeasured, gone before anyone existed to see it. What makes 2029 different, what truly makes it a turning point, is that for the first time we are going to be there. Not merely glancing up, but watching with everything we have, machines and telescopes and human eyes all trained on the same rock at the same moment. And there are two spacecraft in particular that turn this from a spectacle into a genuine experiment. The first has one of the great second acts in the history of space exploration. You may remember a mission called OSIRIS-APEX, the NASA spacecraft that flew to the asteroid Bennu, reached down, gathered a sample of its surface, and sent that sample home to Earth in a capsule that parachuted into the Utah desert in the autumn of 2023, the first American asteroid sample ever returned. That could easily have been the end of the story. The spacecraft had done its job. But it was still healthy and it still had fuel and it was still flying. So instead of retiring it, the mission was given a new name and a new destiny. It is now called OSIRIS-APEX, the Apophis Explorer, and its entire reason for living is to chase down Apophis. The very spacecraft that already proved it could rendezvous with one rubble-pile and touch its surface is now racing across the solar system to meet the most famous asteroid of them all. Because of the unforgiving mathematics of orbital mechanics, it cannot simply park beside Apophis as the asteroid screams past the Earth. Matching that speed in geometry instantly is not possible. Instead, the spacecraft is timed to arrive at the asteroid about a month after the close approach, falling into formation in the quiet weeks that follow, and then settling in to fly alongside Apophis for an extended stay, mapping its surface with cameras and instruments, reading the chemistry of the rock, and watching how it turns in the aftermath of its encounter with our world. And the single most remarkable thing the spacecraft is going to attempt is something it essentially learned how to do at Bennu, and it is the closest we will come to physically reaching inside the asteroid. The plan is for the spacecraft to descend toward the surface, dropping down to within a few meters of the ground, and then to fire its thrusters downward, blasting the surface with its own engines, deliberately stirring up and blowing away the top layer of loose material. The goal is to peel back the weathered skin, to expose the fresher material hidden just beneath, the stuff that has been shielded from the harsh weathering of space, and to study what gets revealed. Think about what that means in the context of everything we have discussed tonight. We have spent this whole journey talking about how the interior of Apophis is a closed door we cannot see through. This spacecraft is going to fly down and, on purpose, blow the dust off a little corner of it. And this is not an untested fantasy. It is being attempted by the same proven spacecraft, with the same kind of instruments and much of the same team, that already touched one rubble pile and brought a piece of it home. The second mission completes the picture, and in some ways it carries the more crucial job because its task is the before. Europe's space agency, working together with Japan's, has built a mission called Ramses, the Rapid Apophis Mission for Space Safety. After years of preparation, it was given full approval and funding at a meeting of Europe's space ministers in late 2025, and it is now being built in earnest. The plan is for Ramses to launch in the spring of 2028 and to arrive at Apophis in February of 2029, roughly 2 months before the close approach. That timing is the entire point. Ramses is meant to get there early so that it can study Apophis carefully before the Earth ever touches it. It will measure the asteroid's shape, its spin, its surface, its exact undisturbed state, establishing a detailed baseline of what this object is like in its quiet, untouched condition. Then it will ride along through the encounter and record what changes. And it will not arrive empty-handed. The plan is for Ramses to carry 2 smaller spacecraft, deployable companions, one designed to study the asteroid up close from orbit around it, and the other intended to actually touch down on the surface of Apophis itself, a tiny lander on the back of the serpent. Among its instruments will be high-resolution cameras able to map the surface down to fine detail and watch for the smallest changes, and a thermal imager contributed by Japan that reads the temperature across the surface, which tells us how the surface holds and sheds heat, which in turn reveals how loose or how packed, how fine or how bouldered that surface really is. Now think about why that before and after design matters so much, because this is the part that elevates the whole endeavor from sightseeing into science. An experiment is only meaningful if you measure the starting condition. If all you have is a picture of the asteroid after the flyby, you can describe it, but you cannot know what changed because you never recorded what it was before. By having Ramses on station 2 months early, taking careful measurements of the spin and the shape and the surface, we create the before. Then the Earth applies its force. Then we measure the after in detail with the spacecraft that remain. The difference between those 2 measurements is the answer to the question we have been asking for 20 years. The difference is the readout of the experiment. We are not merely going to watch Apophis get squeezed. We are going to measure exactly how it responds, and from that response, finally begin to read what it is made of on the inside. And there is a lovely way in which all of this loops back on itself. The thermal measurements that map the surface also sharpen our understanding of that faint Yarkovsky push, which tightens the orbit even further. The heat reveals the surface refines the orbit lets us aim the spacecraft, and the spacecraft read the interior. Every thread in this story eventually ties back to every other. And behind those two spacecraft there will be more eyes still. There are other proposed missions and fast flybys being prepared, including a Japanese probe that may sweep past Apophis even before Ramses settles in, taking the first space-based images of the asteroid in preparation for the main event. There will be the professional observatories of Earth, turning their instruments on the asteroid as it passes, the powerful radar dishes hammering it with radio waves to read its shape and spin at the very moment it is being stressed. The same technique that first revealed its silhouette now trained on it during the critical hours. Telescopes around the world will track its brightness as it tumbles, watching for the subtle flickers that would betray a changing spin or a freshly exposed patch of surface. And then there is the last and most numerous set of detectors, the ones that cost nothing at all to build and that may, in the end, matter most for what this event means to us as a species. Human eyes. Roughly 2 billion of them. Because while the spacecraft do the precise science, the ordinary people of Earth, across much of Europe and Africa and into Western Asia, will be able to step outside on that April evening and simply see Apophis, a moving point of light brighter than the stars of the Big Dipper, gliding across the sky over the course of a single night. That shared act of witnessing is not a footnote. It changes the meaning of the whole thing. For almost all of human history, the sky was something that happened to us, something we could only interpret after the fact, through fear or through myth, and much later through instruments turned on events long after they had passed. On the night of the 13th of April 2029, for the first time, a planet and a small fleet of robotic explorers and around 2 billion ordinary human beings are going to watch the same experiment unfold together, in real time, knowing exactly what it is and what hangs on it. These are the detectors wired up to the closed door. The machines will read the spin and the surface and the hidden interior. The eyes will hold the memory. And every one of them will be pointed at the same question we started with, the question that has been humming quietly underneath this entire story all night long. What is actually inside the serpent? We are about to be in the best possible position we have ever been in to find out. And this is exactly why the stakes of getting it right reach so far beyond this single rock and this single night. The 2029 encounter is, in the truest sense, a free dress rehearsal for what may turn out to be the most important skill our species ever has to learn. Somewhere out there, on some orbit we may not yet have mapped, there is very likely an asteroid that is not going to miss. Not Apophis. Apophis is safe, and I would not have spent these hours with you pretending otherwise. But someday, in some year that no one has yet circled, something is going to be found on a path that genuinely threatens us. And if we ever have to deflect such an object, to nudge it off a collision course before it arrives, the single most important thing we will need to know is what these bodies are made of on the inside. Because you cannot push a rubble pile the same way you push a solid rock. Push a loosely bound heap too hard or in the wrong place and you might not deflect it at all. You might just break it into several pieces that arrive separately, turning one thread into many. The interior is everything. And Apophis, by letting the Earth squeeze it in front of all of our instruments, is about to give us our first real lesson in the hidden mechanics of these objects. A lesson paid for by gravity rather than by disaster. We have, in fact, already taken the very first cautious step in learning to push back, and what we learned only underlines how much the interior matters. In 2022, NASA flew a spacecraft called DART straight into a small moonlet named Dimorphos, which orbits a larger asteroid deliberately at thousands of kilometers per hour. It was the first time humanity ever intentionally changed the orbit of a celestial body, and it worked. The little moonlet's orbit shifted by a measurable amount. But here is the lesson that surprised even the people who ran the experiment. Dimorphos turned out to be a loosely bound rubble pile, and when the spacecraft struck it, it did not simply punch a neat crater. It splashed. It threw out an enormous plume of debris, a great tail of rubble flung into space, and the recoil from all that ejected material actually pushed the asteroid harder than the impact alone would have. The softness of the body changed everything about how it responded to being shoved. Now think about what that means for the day we might actually need to deflect something for real. The way an asteroid responds to a nudge depends entirely on what it is made of inside. Hit a solid rock and it moves like a solid rock. Hit a loose rubble pile and it might absorb the blow or splash or worse, come apart into several pieces that keep coming on slightly different paths. You cannot plan that maneuver without knowing the interior. And we have just spent the whole night establishing that the interior is the one thing we cannot see from afar. So when Apophis lets the Earth squeeze it in 2029, and we watch how its spin shifts and whether its neck moves and how its surface slides, we are not merely satisfying our curiosity about one rock. We are learning to read the kind of object we may one day have to move. This is why the people who study these objects talk about the coming encounter the way astronomers once talked about a rare eclipse. It is a once-in-a-generation alignment of opportunity, a chance to learn something we genuinely cannot learn any other way, on a famous object, with years to prepare. The kinetic impactor, the deliberate punch that Dark proved, is one tool in the toolkit. A gentler approach, sometimes called a gravity tractor, a spacecraft that would hover near an asteroid and tug it almost imperceptibly with its own faint gravity over years, is another. But every one of these tools is only as good as our understanding of what we are pushing. And that understanding is exactly what Apophis is about to hand us, for free, written in the language of its own response to our planet's pull. Step back far enough, and there is something almost philosophical in all of this. We tend to imagine the solar system as a place of solid worlds, of planets and moons and hard rocks moving cleanly through empty space. But the more closely we look at the small bodies, the asteroids like Apophis and Itacawa and Bennu, the more we find that many of them are not solid at all. They are rubble barely held together or piled in stone. We live, it turns out, in a neighborhood of loosely bound debris, drifting on long quiet orbits, occasionally passing close. And one of those piles of debris, named for the Serpent of Chaos, is going to come close enough in 2029 to let our planet take hold of it and, in that grip, finally tell us a little of what it really is. There is a longer perspective worth holding here too, because Apophis is not only a hazard or a science experiment. It is a piece of the beginning. Bodies like this are leftovers, fragments of the raw material the planets formed from more than 4 billion years ago, material that never got swept up into a world. When we study the composition of Apophis, that stony mixture so similar to the meteorites that fall to Earth, we are looking at a sample of the very same stuff that built the ground beneath your feet. The rubble pile passing over the Atlantic that night is, in the most literal sense, a relic of the construction site that made us. To reach out and read its interior is to read a page from the oldest chapter of the entire solar system story, a chapter that is normally sealed away inside objects too small and too distant to ever examine. And maybe that is the part that should stay with you tonight more than any single number or date. We are a species that has mapped this object's path for the next 100 years, that can tell you where a mountain of rock will be on a specific Friday evening 4 years from now, down to the kilometer, after it has traveled hundreds of millions of kilometers around the sun. We are that powerful. And in the very same breath, we have to admit that we do not know what it is made of inside, that our most confident predictions about its behavior come with a quiet asterisk, that we are going to learn the real answer not by figuring it out in advance but by watching in real time and seeing what the asteroid chooses to do. There is a humility in that which I find genuinely moving. We have built the most precise picture of the heavens in all of human history, and it has led us, in the end, to a closed door we cannot open by thinking. Only by waiting. There is something almost unprecedented, when you think about it, in the simple fact that we get to prepare for this at all. For nearly all of human history, the objects that fell from the sky came without warning. A flash, a shock, a crater, and then the slow work of figuring out what had happened, always after the fact, always too late to do anything but survive it or not. Apophis is different in a way that should not be lost on you. We saw it coming a quarter of a century out. We argued about it, measured it, frightened ourselves with it, cleared it, and then turned the whole event into a planned act of science. We are, perhaps for the first time in the long and uneasy history of our relationship with the sky, going to meet one of these ancient visitors entirely on our own terms, with our instruments ready and our eyes open, having decided in advance exactly what we want to learn from it. That is a kind of power our ancestors could not have dreamed of, the power to take a thing that once would have been read as an omen and to turn it, instead, into an experiment we run on purpose. So picture it one more time the way we began, and let the picture be the last thing you carry down into sleep. It is the evening of Friday, the 13th of April in the year 2029, across Europe and Africa and the western edge of Asia. The sun has gone down, the first stars have appeared, And then there is a point of light that does not quite belong, moving, climbing, brighter than the handle of the Big Dipper, sliding across the constellations faster than anything up there should. 2 billion faces are turned upward in the dark. 2 spacecraft hold their careful formation in the silence beside it. And for a few hours, a planet and an ancient piece of rubble meet, the way they have met countless times before across the unimaginable history of the solar system, except that this once, for the very first time, someone is watching closely enough to understand. We will not know exactly what we are seeing until we see it. The most famous asteroid we have ever found is still a closed door, and we have to wait for the Earth itself to ease it open. The serpent has been circling quietly ever since the night we first caught it on a mountaintop in the desert. In 2029, it comes close enough to touch. And whatever it does when our planet finally takes hold of it, whether it barely sighs or shifts in some small visible way, it will do once, in the dark high above the ocean while the whole world looks up. Rest easy tonight. The sky is not falling. It is simply, for once, letting us come close enough to learn.